Hello everyone, I'm Onur Dizdar from Imperial College London. I'm here to summarize our work titled Right Splitting Multiple Access for Joint Radar Communications with Low Resolution DACs. This is the outline of my presentation. I'm going to start by a brief introduction. Next, I will give the details on our problem and the proposed solution. Then I will present some simulation results and conclude my presentation. Joint radar communication systems share the common spectral and hardware sources to efficiently use the limited radio frequency spectrum. For multi-antenna JRC systems, it's important to manage the interference among the communication users and radar targets efficiently, and also reduce the hardware complexity and increase the power efficiency. The use of low-resolution digital-to-analog converters is an important method to achieve such targets. However, operating DACs with low resolution degrades the quality of the transmit signal and so the actual rate in the system. Our motivation in this work is to simultaneously perform multi-antenna, multi-user communications and sensing efficiently under the degrading effects of low-resolution DACs. Now we take a look at the multi-user, multiple input, multiple output communication methods. Multi-user MIMO is a key technology for current and emerging wireless communication standards, such as 5G New Radio, to meet the demand for increasing data rate and accessibility. The most common form of multi-user MIMO is space division multiplexes, which achieves an improved sum rate with perfect channel state information at the transmitter. SDMA relies on linear precoding to separate user streams at the transmitter and treats multi-user interference as noise at the receivers. However, it suffers from a severe performance degradation under interference due to imperfect CSIT. Another form of multi-user MIMO is non-orthogonal multiple access, which is based on superposition coding at the transmitter and successive interference cancellation at the receivers. In NOMAP, the user with the stronger signal fully decodes the interference, while the user with the weaker signal fully treats it as noise. It has been shown that NOMA suffers a significant degree of freedom loss in multi-antenna systems unless user channels are aligned and have a disparity of strength. A relatively recent form of multi-user MIMO is rate-splitting multiple access, which is based on linearly precoded rate splitting at the transmitter and successive interference cancellation at the receivers. RSMA splits user messages into common and private parts at the transmitter. At the receivers, it partially decodes the interference and partially treats it as noise. It has been shown that RSMA achieves the entire DOF region of K-user MISO broadcast channel with imperfect CSIT. We explain RSMA over an example with two users. At the transmitter, the messages of two users are split into two parts, the common parts and the private parts. Then, the common parts of the messages are combined into a single common message. The combined common message and the two private messages are independently encoded into separate symbol streams. The transmit signal is obtained by applying linear precoding to each symbol. At the receiver, successive interference cancellation is performed over the received signal. First, the common message is decoded by treating the interference from private symbols as noise. Then each receiver decodes its own private message by treating the private messages of other users as noise. The maximum rates for the common and private messages can be written as given here accordingly. Now we define our system model. We have a transmitter that aims to perform communications and radar operations simultaneously. The transmit signal is composed of linearly precoded RSMA data symbols for the multiple users. After splitting and linear precoding, the transmit signal is quantized by DACs employed at each RF chain connected to the antennas. The quantized transmit signal is a scaled version of the non-quantized transmit signal with an additive quantization noise term. Scaling factor and the additive noise variance are dependent on the number of quantization bits employed by a DAC. We assume that all DACs at the transmitter operate with the same number of bits. The power consumption of a single DAC is also dependent on the number of quantization bits and a DAC power consumption coefficient. We formulate an optimization problem to find the optimal precoders that maximize an objective function. Our objective function is a combination of the sum rate of the communication system and the least squares error of the radar beam pattern probing power with respect to a desired mask under the effect of DAC quantization. The parameter lambda, which is also called the regularization parameter, adjust the priority of the radar beam pattern error with respect to the sum rate in the design criteria. We also have several constraints in our optimization problem. The first constraint ensures the decodability of the common stream by all users. Here, CK denotes the rate of the common part of the splitted message of user K. The second constraint is related with the total transmit power budget. This constraint ensures that a total power transmit budget is shared between the precoders and the DACs at each RF chain. The constraint also ensures that the power at each transmit antenna is equal in order to limit the nonlinear impairments on the transmit signal. The optimization problem we formulate is non-convex due to the non-convex sum rate maximization in the objective function and the quadratic equality in the power constraint. We propose a solution for the problem based on alternating direction method of multipliers. In accordance with the ADMM approach, we divide the problem into two parts. In the first part, we solve the non-convex problem of sum rate maximization with the additive augmentive Lagrangian parameter by weighted MMSE alternating optimization method and obtain the updated precoder vectors. In the second part, we solve the non-convex problem of radar beam pattern error minimization with the additive augmented Lagrangian parameter under the total transmit power budget constraint by semi-definite relaxation method and obtain the updated precoder vectors. We iterate in this manner until a convergence condition is satisfied. We analyze the performance of the proposed solution by simulation results. We first check the convergence of the algorithm, which can be seen in this figure when the radar beam pattern error minimization is prioritized by setting lambda as 10. For this result and the rest of the results in the presentation, we consider 4 transmit antennas, 2 communication users, and 1 radar target. The total transmit power budget is taken as 1 watt. The DAC power coefficient is taken at 100 microwatts, and the noise varies is 10 microwatts. We consider sum rate and normalized mean square error as evaluation matrix. Normalized mean square error is defined as the radar beam pattern error divided by the total power of radar beam pattern mask. We consider independent radar fading channels for both users. The figures show the performance metrics with varying number of quantization bits. As observed from the figures, RSMA achieves significantly higher sum rate than SDMA for similar normalized mean square error values, approximately 8 bits at the optimum point. An interesting phenomenon is that the sum rate increases up to a certain number of quantization bits and then decreases. This is a result of the transmit power budget. As the quality of the precoders increase with increasing number of bits, the sum rate tends to increase. However, increasing the number of bits also increases the power consumption of the DACs, which in turn decreases the power allocated to the precoders. After a certain number, increasing the quality of the precoders does not affect the sum rate as much as reducing the power allocated to the precoders. So the sum rate tends to decrease after such a point. This figure shows that we should not operate with the maximum number of quantization bits if we want to achieve the highest sum rate under a total transmit power constraint. We move to the results, demonstrating the sum rate performance with respect to normalized radar beam pattern error for different number of DAC bits. Smaller normalized MSE on the figures show the regions where the radar beam pattern design is prioritized. We see that RSMA achieves a higher sum rate than SDMA, especially when the radar beam pattern is prioritized. This implies that RSMA manages the interference due to radar beam pattern designed under the equal power constraint better than SDMA. The gain improves as the number of quantization bits is increased from 4 to 6, and it's almost 8 bits. For 8 and 10 quantization bits, we see a similar trend. The sum rate gain of RSMA is approximately 7 bits compared to SDMA. The reduced gain here is due to the decreased operating SANR, which decreases due to increasing DAC power consumption and DAC decreasing precoder power. In conclusion, we investigated RSMA in a joint radar communication system using low-resolution DACs under a total transmit power budget. The optimal precoders showed that RSMA outperforms SDMA by managing the interference due to radar beam patterns efficiently. We also showed that The highest sum rate is achieved at a specific number of bits that is less than the maximum possible number under the total power budget. These are our references. Thank you very much for listening.